little messy this morning. All right. So, what we did was we started to talk about the whole solution process. Well, that's weird. Why did that get moved? Hang on just a second. It's interesting. I updated the software that runs all this, and for some reason, oh, I see what the issue is. Okay. It has nothing to do with what you're seeing. Hopefully my head's on the right. For some reason, Zoom has flipped my camera around, and I don't understand that. All right, so what we did was we left off with solutions or gases in solutions. And what we concluded from this was that most gases, at least all the ones in examples, and we talked about some other examples as well, but most of them behave in the way that if you increase the temperature, the solubility of a gas goes down. Okay, and that makes sense from a kinetic molecular standpoint as well. All right. So, and we talked about that in the context of carbonated beverages, which is probably where it's most relevant, at least in day-to-day life. But you do see this, all right? Gases will not dissolve as well at high temperature as they do at low temperature. And that's pretty much what we're going to say, or all we're going to say about the solubility of gases in this chapter. What's far more important and far more interesting to us is what we see with solids, or the solubility of solids in water. And the general trend, as you can see from this graph, is that what we see is that as we increase temperature, we can presume that the solubility of most solids will also increase. In some cases, like if you look at glucose or sodium acetate, the increase is quite sharp. All right, so what this implies is that perhaps there are a number of factors that come into play here. All right, if I look at both sodium acetate and glucose we talked about at the end of last chapter as exhibiting hydrogen bonding between its molecules. There are all these OH groups on glucose molecules. And the temperature effect on those must be significant because we see the solubility of glucose just go way, way up. In fact, it goes off this chart at or below 40 degrees Celsius. On the other hand, if I look at a compound like sodium chloride, I see a very limited increase in solubility with temperature. Okay, the solubility of NaCl does go up a little bit, but not very much between 0 and 100 degrees Celsius. And then we have some oddballs, and the one that's listed here is cerium-3 sulfate. All right, its solubility actually goes down. So there are a whole bunch of factors that influence the solubility of compounds in water. And again, most of the examples here are ionic compounds. But what you can say is generally what you can assume is that as you increase the temperature of water, you can dissolve more of an ionic substance. The other thing you can think about, and this is one of the ways that ionic substances are separated from one another in aqueous solution, is that cooling a solution has a more marked effect on solubilities of some salts over others. It's one of the ways that you can separate, say, a solution of sodium nitrate from that of sodium chloride. If you have a mixture of those two salts in solution, you could bring the solution up to a really high temperature and saturate it with sodium nitrate and then cool it down to the point where the sodium nitrate will start to come out of solution. And what you'll be left with then is a solution that has more sodium chloride in it and still some sodium nitrate, but you could bring out, or you could purify out pure sodium nitrate that way. The other thing that this can accomplish is that you can make things like rock candy with glucose, and that's how it's done. You make a saturated solution of glucose at a high temperature, and then you cool it down slowly. And as it cools slowly, you form these really nice looking crystals of glucose. And that's what rock candy is. It's just crystalline glucose. All right. So next thing we're going to do is we're going to do some review. All right. Most of what I'm going to cover here comes straight from chapter 4. And what we're going to do is we're going to expand on it a little bit. All right. You talked about concentration units back in chapter 4, and you talked about the utility of them. And that's certainly something we're going to build on in this course. We are going to use concentration units pretty much for the remainder of the semester in different applications, and particularly with regard to chemical equilibrium, which we're going to start once we get into chapter 15. But we need to review some of these concentration units, and you can guess what some of them are because you need to be comfortable using them. But in the context of this chapter, what we're going to do is we're going to look at relationships between certain properties of solutions and these concentration units of solute, or in one case of solvent. So let's begin. The first one you have seen before, and again, maybe or possibly unknowingly, and that is percent by weight or percent by mass. And basically what you can think about is it's the part divided by the whole. All right, and that's the way most concentration units work, although there is one exception, as we will see. But if I want to figure out a percent by weight of a solution, one of the ways I can do it is take the mass of the solute. I could also do this for the solvent if I wanted to. But generally speaking, we talk about the solute divided by the total mass of the solution times 100. All right. Another way that's useful to look at this is to say instead, well, okay, if I have a certain percentage of solution, what it means is that if I have 100 grams total of the solution, I have the percentage mass in grams of the solute. So if I have a solution that's 30% sodium chloride by weight, what that means is if I had 100 grams of that solution total, the mass of sodium chloride in that 100 grams of solution would be 30 grams. Now, there are some issues that come up with this that we sometimes have to deal with, and that is that a unit such as this does not account for volume of solution. And that's typically how we deal with things when we're in lab. We measure by volume. It's not as practical to measure solutions by mass as it is by volume. And so if you're going to make any conversions from mass percentage to some other concentration unit, as we will do, you're going also to need the density of the solution. You need to know that. All right, but this is useful, and there are times what's really bizarre about this, and again, it probably comes down to convention more than anything else, is that solutions of acids like hydrochloric acid or acetic acid or sulfuric acid are sold commercially in percent by volume, which is kind of strange. And that's probably the most common place you see it. We buy concentrated acids because it's the cheapest way to do it. And then what we do is we dilute the acids on site. And that's the way most people do things because you pay, otherwise you're just paying for shipping of water. And so why not just buy the concentrated solutions and dilute them down? But it does pose some logistical issues that you have to think about. And this is something we will touch on in a few minutes. Before we go there are a few other things we have to talk about. I present this one not so much because it's relevant to this course, but because it's relevant in other parts of our lives. Right? If I'm going to talk about a solution that's percent by volume, the first thing that implies is that both solvent and solute are liquids. in the case of percent by volume, the most practical application of it, as far as we're concerned, is when we talk about alcoholic strength of beverages. All right, the United States has very strict laws about how liquor concentrations are reported. Other countries do the same thing, although the laws are different. Okay, but generally, any government feels the need to regulate alcohol in some way, shape, or form, and some much more draconian than others. There are nations where it's technically illegal to possess alcoholic beverages. All right, that was the case in the United States during a period in the 1920s known as Prohibition. And the U.S. rescinded that. It was actually an amendment to the Constitution, and it was eventually repealed because it was found to be impossible to control. So, in the U.S., if you market something as a wine, okay, and there's certain other criteria that must be met, but there are labeling criteria. And one of the labeling criterion is that you must report the percentage of alcohol in the wine in a certain size and in a certain place on the label. Okay, if you look at any wine labels, you'll notice that the percent by volume is there. It's either on the front label, but much more often it's on the back label, and the size is regulated. And that has to be there. It's required by law. And so the easiest way to measure alcohol is by specific gravity. And if you do that measurement correctly, you get percent alcohol by volume. All right, so it's very easy to do with wines. And of course, so that's what's done. And again, it gives you an idea of the strength of the wine. And the other thing is that there are certain parameters in terms of percent by volume that must be met in order for a beverage to be marketed as wine versus being fortified or, in the other case, beer. All right, so what is percent by volume? Well, again, it's the volume of the solute divided by the total volume of the solution. Now, this is a little bit deceptive with alcohol because when you mix alcohol with water, the total volume is not the total volume of the two liquids. There's a little bit of contraction when you do it. But nonetheless, this is what's used. And of course, you can have percent alcohol anywhere from 0 to 100. Another way of thinking about it is if you consume 100 milliliters of a beverage, how many milliliters of alcohol are you consuming? And that's probably more useful for day to day because you definitely want to regulate how much alcohol you take in, depending on what you're doing and depending on other things. All right. Now, the interesting thing is in the US, if you market something as a distilled spirit, then what you have to do is you have to write or you have to print on the label the proof. And the proof is percent V volume by volume times 2. All right, again, that's an old tradition. And the reason is if you're distilling spirits, a proof has to be measured using specific gravity as well, but it uses a different type of specific gravity measurement. And that was convenient back in the bad old days. Now you can do all of this from refraction, and it's much easier. And you don't have to worry about these conventions, but they've stuck because that's the way the law is written. So actually what a lot of distillers have done is they report both values on the label. They have to report the proof by law, but they often will report percent alcohol by volume, especially if they market in other countries, because other countries do not allow proof. They want percent by alcohol, which makes more sense to me. The other interesting thing is in the US, it is still illegal to report percent alcohol by volume on beer labels. right? That's the way the law is written. And that law was written after Prohibition was repealed. And the thought was that people would just buy stronger beers. It turns out that's not really the case. And what's interesting is the BATF has said, okay, that law is on the books. It's technically illegal to report percentage of alcohol by volume in beer, but we won't enforce it. And so a lot of breweries are putting their alcohol by volume on their beer labels anyway, even though technically it's illegal. All right, so of course we have our graphics showing the different things. Okay, another concentration unit that you've seen before very likely is percent mass volume. This is a really strange one, but it has a very direct application. All right, basically what it is it's a way of gauging how much of a solute can be dispensed in a certain volume of solution. And it's used extensively in the medical profession. All right, a standard IV bag. This is a D5W bag, which is kind of commonplace if IVs are given. Okay, there are of course other ones as well. But D5W means 5% mass volume dextrose, which is glucose, in water. So that means if you inject 100 milliliters of this solution into a patient, you're giving that patient 5 grams of glucose. Okay, another thing that you'll notice is if you look carefully at this label, which may not be so easy to see online, it also shows mass volume of sodium chloride. Right, and that's something we'll talk about later. It's very important that if you're injecting solutions into patients, especially large volumes, that the concentrations of the things that go in through the needle into the bloodstream are similar to what already exists in the bloodstream. Otherwise, it can be excruciatingly painful and possibly harmful to a patient if you're injecting a solution that does not have similar concentrations. And so this is considered what's isotonic. And we'll explain some of the factors associated with that when we get into colligative properties. Okay, far and away, the most important concentration unit in a chemistry class is molarity. And it's something you have learned to deal with before. And again, you will be using it extensively in this course as well as in Chem 126 if you're taking Chem 126 this semester. Molarity is defined as moles of solute per liter of solution. So in some ways you could argue that it's the same type of concentration unit as mass percent volume. Basically, what it does is it gives us a way of counting the moles of solute based on the volume of solution that we have dispensed. And that's what's very useful for us, okay? You have molarity equals moles of solute per liter of solution. Or another way of thinking about it is if I multiply the molarity of the solution by the volume of solution in liters, that's going to give me the number of moles of solute in that solution. All right, that's one way we could approach this. Another way we could approach this, which we will be using later in the semester, is if we multiply the molarity of a solution times the volume of the solution in milliliters, that will give me millimoles of solute. All right, there are times when that's very useful, and some of you might have seen that when you did titrations last semester in Chem 125, or even in Chem 121. I do present this when I talk about titrations in Chem 121. We will be doing more titrations at the end of the semester, and this idea of the millimole is a very useful thing for us. Okay. Another thing to think about is, and this is something we covered, at least in my lab this week, is if we want to do dilutions, all we have to do is multiply the molarity of and times the volume of the concentrated solution to give us the molarity times the volume of the diluted solution. Because when you make a solution, or when you dilute a solution, what you're doing is you're just adding more solvent to it. You have the same number of moles in both cases. Molarity times volume gives you number of moles. All right. So, one of the tools of the trade of precise concentrations is the volumetric flask. And again, that's something you've probably seen in Chem 1. You'll certainly see it again in Chem 2 lab. We use volumetric flasks several times in Chem 126. All right, but again, you want to be familiar with molarity and the calculations involved with it. Okay, here's another one you've seen before. Mole fraction. If you think back to chapter 10, you talked about mole fractions of gases, and that's really where it's most relevant. However, it will appear again in this chapter. All right, if we're going to calculate the mole fraction of something, what we do is we take the moles of that component. And I'm not specific here because it could be mole fraction of solvent or of solute. All right. You take the moles of whatever substance in question, whether it be solvent or solute, and you divide that by the total number of moles in solution. In the past, you used this to determine partial pressures of gases using Dalton's law of partial pressure. We're going to use a different application here, although this is the one that we'll talk least about in terms of colligative properties. Another concentration unit that you need to be aware of, and it's really specifically for this chapter that you need to think about it, is molality. Now, we denote molality with a small m. A lot of books and homework sites use an italicized small m as opposed to a small m like I've done here. Okay, so as not to confuse molality with meters. Right? I would say the best thing you can do is not to worry so much about symbology, but look at context. All right. As far as we're concerned, the most likely context you're going to see molality is in colligative properties. There are two colligative properties we're going to discuss in a little bit that are related directly to the molality of a solution. Okay, now, here's the strange thing. If you were to take a course that focused exclusively on SI units, molarity is the SI unit of concentration. Okay, because it uses SI units, other SI units of measurement. And this goes back to chapter 1 when SI units were first discussed, and probably the only time they were discussed in chemistry courses. We talk about them, but we don't use them. And the reason we don't use them is because for our intents and purposes, they are impractical. Who's going to measure a concentration of solution this way? Okay, basically it's moles of solute per kilogram of solvent. Once you've made the solution, it's really difficult to measure anything with it. You can't do dilutions in the same way you can using molarity or even mole fraction for that matter, because the difference here is it's amount of solute per amount of solvent, whereas all the other concentration units we've covered this morning or this afternoon are amount of solute per amount of solution. All right, so molality is strange. If you take physics courses, molality appears if you're talking about concentration units. The only time I ever used it outside of this chapter is when I took a physical chemistry course. All right, it just doesn't really work very well. Who's going to measure out a kilogram of solvent in a lab? Okay, liters or milliliters of solution are much more useful measurements as far as a chemistry lab is concerned. However, because of the colligative properties that we're going to discuss, we have to talk about molality in this chapter. And this is the only time you're going to see it in this course. All right, so let's do a little bit of work. See if you can take a few minutes to figure out this question. Okay, I want to make a solution by dissolving 5.85 grams of sodium chloride into 75.4 grams of water. What's the percentage of the solution by mass if I do this? What am I going to do to figure this out?
Would you divide the 5.85 by the sum of 5.4?
But isn't it mass of the part divided by mass of the whole? So,
So
yeah,
add those two?
exactly. So what you would do is you'd take the 5.85 grams, the mass of the solute, and then divide that by the sum of the two. So it would be 75.4. That's the mass of the solvent plus the mass of the solute. And then you'd multiply that by 100. So another way of thinking about it is if you want to save keystrokes on your calculator, you just divide 5.85 by 75.4 plus 5.85, and then you just slide the decimal place over 2 places to the right from your answer. So if I do that, yes, you got it. 7.2%. So there we go. All right, so you get an idea of this. And again, this is a very infrequent way of viewing percentages, but again, it illustrates something that you need to think about. All right, here's a similar sort of thing. Okay, if we dissolve 25.1 grams of sodium chloride into 100 grams of water, to get our percentage, we're going to take 25.1 grams and we're going to divide it by the sum of the two, which is 100 grams of water plus 25.1 grams of sodium chloride, and then we're going to multiply that by 100. And if we do that, what do we get? Yes. So the correct number is sig figs. 20.1 would be the correct answer. Okay. Very good. All right. So let's do some review of Chem 1. I mean, really, that's review as well. But this is far more important. If I take 15.115 grams of copper 2 sulfate pentahydrate. Okay, so think about this. If you were doing this in lab, what would you do? You'd weigh out 15.115 grams of copper 2 sulfate pentahydrate. You'd transfer that into a volumetric flask that has a volume of 200 milliliters, and then you'd fill the volumetric flask so that the meniscus is on that 200 milliliter line, seal it up, and shake it up, and you have your solution. So we have several things we have to think about here. Okay, the first one is, if we're dissolving copper 2 sulfate pentahydrate, what's the formula of that compound? This is stuff I expect you to remember, because we talk about compounds by name quite frequently in this course, on the presumption that you have learned and remembered at least some of the nomenclature from chapter 2, which is where this came from.
Is it Cu and then the parentheses SO4 and then, well, no, copper and sulfate both have -2.
Yeah, copper 2 is +2 and sulfate is -2. So yeah, you're correct. So you'd say, all right, it's CuSO4, one of each type of ion. But what does the pentahydrate mean?
It has 5H2.
Yes. Okay. And so this is one of the things we have to think about. If we're weighing out this compound as the pentahydrate, that means the waters of hydration are included in what we're weighing. So when we figure out the molar mass of this, we have to include the 5 waters of hydration. All right, so we can refer to our periodic table, which, yeah, there we go. Okay, we've got a periodic table up. So take a look, see if you can figure out what is the molar mass of copper 2 sulfate pentahydrate versus, or based on this. Copper is 63.55 grams per mole. Hydrogen is 1.008 grams per mole. Oxygen is 16 grams per mole, 16.00, and sulfur is 32.07 grams per mole. What do we get for a molar mass of copper 2 sulfate pentahydrate if we add those together? Sounds good. Yes. 249.67 grams per mole. All right. So what are we going to do next? We know the molar mass of copper 2 sulfate pentahydrate. We know how much copper 2 sulfate pentahydrate we're weighing out. How do we get number of moles from mass and molar mass? Yeah. Yes. So that means in this case, we're going to take 15.115 grams of our CuSO4.5H2O, and we're going to divide that by the molar mass. All right. Now, that's going to give us number of moles. We could stop there and do one more step, or we could just continue and say, all right, we're going to dissolve that into a total of 200 milliliters of solution. What volume of that solution is, or what is the volume of the solution in liters if it's 200 milliliters? Yes. So I just divide my 200 by 1,000, which means I move the decimal place over 3 places to the left. And so if I just take that number of moles and I divide it by the volume of the solution I have in liters, that's going to give me my molarity. So I'm going to take 15.115 divided by 249.67 and then divide it again by 0.2. If I do that, I get 0.3027 molar. Or if I want to spell it out, I could say moles of CuSO4.5H2O per liter of solution. Okay, and that's very useful. Again, some of you are taking lab this semester. I know because I've seen your faces in lab. We did this with the spreadsheet in part 2 of the Excel lab. You said, okay, you have a certain mass of a certain solute. What's the molarity of that solution? Now, there's one other thing that's very useful here. And you've probably seen this before. What gives rise to the color of the solution of CuSO4.5H2O? It's a blue solution. Okay, it's a little bit lighter blue than the color of pen I'm using in this drawing. Okay, and perhaps it's more closely related to this light blue one. Here's a question I could ask you. This particular molarity, at least based on the way we calculated it, is the molarity of the whole solute. But we know this solution is blue colored. The copper 2 ion is what gives rise to the blue color in solution. So here's what I could ask you. I want to figure out the concentration of the copper 2 ion given the molarity of this solution. How am I going to do that? I should say this is 5H2O. How do I figure this out? Here's what I want to think about. What happens when I dissolve copper 2 sulfate pentahydrate? It's an ionic compound. So if I dissolve this ionic compound in water, what do we say happens to it? What happens to ionic compounds in general when we dissolve them into aqueous solution, when we dissolve them into water? What did we learn back in chapter 4?
They separate into their ions.
Yeah, they dissociate. We form an electrolyte solution. Okay, so in this particular case, what's going to happen is this formula basically is going to fall apart. I get copper 2 ion in solution. I get sulfate ion in solution. And I also get 5 waters. That's if this thing completely dissociates. This is a little bit of a stretch. But here's what's important. Based on this, if I start with 1 mole of copper 2 sulfate, this balanced net ionic equation tells me I'm going to get 1 mole of copper 2 ion in solution. And so therefore, what I would say is, all right, if this solution is 0.3027 molar CuSO4.5H2O, it also means that the molarity of the copper 2 ion in solution is the same. Now you did this, if you did the cobalt lab in Chem 125, it's exactly the same sort of thing. The thing is, not all salts are 1-to-1 like this. If I had sodium sulfate instead of copper 2 sulfate, then if I had a 0.3027 molar solution of sodium sulfate, the concentration of sodium ion would be twice that, because each mole of Na2SO4 that dissolves in solution produces 2 moles of sodium ion. All right, that's one thing. Another thing I want you to think about with regard to this is this notation, because we're going to see this an awful lot later in the semester, starting with the next chapter. If I put an ion or a compound in these square brackets like this, the implication is that I'm looking at the concentration of that ion or of that compound in square brackets in moles per liter. All right, so if I write copper 2 ion in square brackets, as I have done here, the implication is I'm looking for what is the molarity of copper 2 ion in a given solution. In this particular case, we already figured that out. So that's something you'll be seeing quite a bit in coming chapters. All right, so there you have it. And again, this is all 100% review, except for the square brackets notation. That's something you probably haven't seen before. All right, let's do one more concentration calculation directly, and then we're going to have to look at some conversions. If I take 25 grams of glucose and I dissolve them into 500 grams of water, I want to figure out what is the molality of this solution. Okay, I'm not looking at the molarity anymore. I'm looking at the molality. And so, again, the definition that we're looking for here is this: how many moles of glucose, which has the chemical formula C6H12O6, are there per kilogram of solvent, which is water in this case. So it's not the total volume of the solution anymore, it's the mass of the solvent. And again, the only time you see that is when you're looking at molality, as you are here. And again, the only time molality is going to have any relevance as far as this course is concerned is in this chapter. So, how am I going to figure out moles of glucose? If I'm starting with 25 grams of glucose, how do I go from grams to moles?
Divide by the molar mass.
Yes, I'm going to divide by the molar mass. What is the molar mass of glucose? If the chemical formula is C6H12O6.
Is it 180.16?
Yeah, that sounds good. Probably for this one, 180 would do, because we only have 3 sig figs in our mass measurement. But we can round that back later. All right. So that's going to give us the moles of glucose. And then again, what we could do is we could take that number of moles of glucose and divide it by the mass of the solvent in kilograms. If I have 500 grams of water, I could divide that by 1,000. And that gives me the mass of my solvent in kilograms. And so I'm going to take 25 divided by 180.16 divided again by 0.5, which is the same as multiplying by 2. And I get 0.278. And that would be molal. Okay. Another way of approaching this, if you want to be specific, is to spell the units out. What does this mean? Moles of glucose per kilogram of water. There are times when that's useful. Okay, and we'll see some examples of those, especially as we get into colligative properties. All right. So let's go back to this idea of commercially available acids. If you buy nitric acid, sulfuric acid, acetic acid, or hydrochloric acid commercially, it's often sold to you as a percent by mass solution. Okay, hydrochloric acid is sold as a 35% by mass solution. Nitric acid is sold as a 70% by mass solution. Acetic acid is often sold as 100% by mass. All right, it's known as glacial acetic acid. And sulfuric acid is most readily produced as a 98% solution by mass. All right, if you look on the label of the bottle, most manufacturers also tell you that the specific gravity of that solution is 1.83. Now, a specific gravity doesn't have any units, but what is specific gravity related to that does have units? And what's the relationship? Does anybody remember what is the definition of specific gravity? It goes way, way back. And it's not often used anymore, but there are some applications. Again, in alcohol production, specific gravity really comes into play because you can measure it quite easily. What's the definition of specific gravity?
Density?
Yes, exactly. It's related to density. So what can we say? We can say this. Specific gravity is equal to density of whatever it is. Okay, in this particular case, you'd say it's the density of the solution divided by the density of water. So what is the density of water? What is it really close to? Numerically speaking. What is the typical density of water?
987.
Yeah, well, okay. 987, what are the units of that one? That's kilograms. Yeah, you probably looked that up online, right? Okay, that's fine. Yeah, no, that's fine. Okay, for our intents and purposes here, what we're going to say is that's pretty close to 1 gram per cubic centimeter, or 1 gram per milliliter, because a cubic centimeter and a milliliter are the same thing. All right. The units you use are kilograms per cubic meter, which is the SI unit of density. And to get a more practical unit of density for our intents and purposes, we're going to take that and divide it by 1,000. So at room temperature, the density of water is about 0.987 grams per cubic centimeter, or grams per milliliter. But this doesn't have to be a very precise calculation, so we're just going to use 1. And so what we could say here is that means for this solution, the density of the solution is roughly the same as the specific gravity. It has a density of 1.83 grams per milliliter. All right, now why do we need that? Well, we have to do 2 things with this commercial solution. And this is very practical. Actually, one of them is not very practical, but the other one is. Oftentimes, if you look at the solutions of sulfuric acid that we use in lab, and you might think back to last semester when you took Chem 125 or whenever it was, this is something you saw. You used diluted sulfuric acid in several labs in Chem 125. And we will use it again in several labs in Chem 126. All right, we don't use concentrated sulfuric acid. It's just too hazardous to handle. And so, in order for the lab coordinators to make up diluted solutions, they need to know what the molarity of the concentrated solution is. Okay, now this is a little bit of a stretch because, first of all, if a solution is 98% by mass, H2SO4, then by the definition we used before, water is not the solvent. Water is the minor component. But we're going to treat water as the solvent because if we're going to dilute this solution, that's what we're going to do with it. So, here's what we want to think about. We want to calculate the concentration of this solution in terms of moles of H2SO4 per liter. Okay, that's one calculation we're going to do. Another one we're going to do, and I'm going to give myself some space here, is we also want to figure out what is the concentration of this solution in molality, or moles of H2SO4 per kilogram of my alleged solvent, H2O. All right, so let's start with molarity first. How do we calculate the molarity of this solution? All right, here's what we know. If I have a 98% solution of H2SO4 by mass, that means this. I have 98 grams of my solute, which is the H2SO4, in a total of 100 grams of solution. Okay, so how do I go from those units to moles per liter? Well, the first thing we could do is say, all right, I want to figure out if I want to change grams of H2SO4 to moles of H2SO4. So that means I'm going to divide by the molar mass. Now, if I go and I figure out what the molar mass of H2SO4 is, it actually comes out to 98 grams per mole. All right, we could be a little bit more precise than that if we wanted to, but this isn't going to be a very precise calculation. There are only 2 sig figs in it based on the percentage. All right, so basically what this tells us is that another way of thinking about this is if I have 100 grams of this stock solution of H2SO4, I've got 1 mole of H2SO4 in it. All right, so at this point, what we can think about is that grams of H2SO4 have canceled. All right, so we could look at this solution in that way, but that's not our goal here. The next thing we have to think about is, well, we need to change, we've changed grams of solute to moles of solute. That's good, okay? That's what we want. how do we change grams of solution to liters of solution? And that's where the density comes in. If I multiply this by the density, then that's going to give me the units moles of solute per milliliter of solution, okay? Because now grams of solution will cancel. And so the only other thing I have to do to complete this calculation is to change milliliters to liters. How many milliliters are there in a liter?
1,000.
Yes. So in this case, that means if I want liters of solution on the bottom, and I actually should spell this out in my end unit as well, because I want it in liters of solution in the bottom of the fraction. That means I'm going to multiply whatever combination I have before by 1,000. And so if I take 98 divided by 100 divided by 98 times 1.83 times 1,000, I get 18.3, but it's going to round back to 18 because there are only 2 sig figs in the concentration percentage, the percentage concentration. So this solution is 18 molar. At least by these standards. And if I know that, then I can do dilutions with it. All right, now my dilutions are not going to be very precise. And this is one of the other issues that you run into with all commercial acids. Even though these solutions are sold as a certain percentage, the percentage is not very precise. It's usually not more than 2 sig figs, maybe 3 in some cases. If you're going to make up very precise concentrated solutions, and this is something that was covered in one of the labs in Chem 125, you have to do what's called standardization. And some of you had that experience with HCl, or excuse me, with sodium hydroxide and with sulfuric acid solutions. You were given solutions whose concentrations were known roughly, say maybe to 1 or 2 sig figs, but you had to go and use a titration to figure out, okay, let's get a much more precise concentration of that solution, say to 4 sig figs. And you did that. All right. So that's how we change percent by mass to molarity. We can't do that calculation without knowing the density of the solution. And in the context of a problem like this, all you have to do is take the specific gravity and change the units to grams per milliliter. That's adequate for it. All right. It's not as precise as it could be, but you don't need that precision for a calculation like this. If your molar, or if your initial percentage is much more precise in the first place, then you would have to do that. All right, so let's move on. Now, the next thing we have to do is figure out what is the molality of this solution. That's a little bit different. Because in the case of the molality, what we want to think about is we have to look at the percentage in a different way. Okay? Molality is defined as amount of solute per kilogram of solvent. Okay, amount in moles. So we do have to figure out the number of moles of H2SO4. But here's what we have to think about. We have to look at this original solution in a different way. Up here, we took mass of solute per mass of solution. But now what we're going to do is this. We're going to say, all right, how much solute is there for how much solvent. So if I have 100 grams of solution and 98 grams of those 100 are solute, as they are in this case, that means the remaining 2 grams of that 100 are solvent. All right, so that's the first difference. If you're going to go from percentage by mass to molality, you have to change that denominator into mass of solvent. And you do that by subtracting the mass of the solute from 100 grams. Okay, so if I have 100 grams of this sulfuric acid solution, it's 98 grams sulfuric acid, 2 grams water. All right, so the next thing I'm going to do is I'm going to divide by the molar mass again. I'll just use 98 because, again, this isn't going to be very precise. Okay, now, do I need the density in this calculation? And the answer is no. I don't have to make that transition from mass of solution to volume of solution, nor do I have to make the transition from mass of solvent to volume of solvent, because I have mass of solvent in my final target. So the only other thing I have to do is change grams of solvent to kilograms of solvent. And I want that kilograms of solvent to be in the denominator. And so what it ultimately is telling me is I'm going to multiply by 1,000. So I'm going to take 98 divided by 2 divided by 98 times 1,000. And in this case, I'm only going to have 1 sig fig because of the 2 grams of water. So this is going to be 500 molal. Okay, and the only sig fig is that one. All right, so in this particular case, the molarity and the molality are vastly different. And that's because we have such a small amount of solvent present in this solution. If you have solutions that are 50% by mass or less, then you would expect the molarities and the molalities to be more in line with one another. Okay, and you can convert from one to the other using this same methodology. All you have to do is to know the density of the solution. All right, and there probably are some ALEX problems associated with that. All right, but again, you want to know this methodology for the first exam. You want to be able to make this transition because occasionally you have to do it. And that's why I illustrated it here. I have some practice sheets for you to try as well on this section of the chapter. Okay, remember we talked about that on Wednesday of last week. I have a practice sheet for chapter 11. All right, I will post that on Canvas. You can start to look at it. There are 6 different versions of it. They cover some of the questions that you can expect on that first exam. And the first exam is a week from Wednesday. It will cover chapters 11 and 13. Okay, again, we don't cover chapter 12 in this course. So let's continue with chapter 13. We're going to make a big inroad into it today, and we'll finish chapter 13 on Wednesday, and then I will have some worksheets for you to look at for that in preparation for the first exam. The other thing I've done for both or I will do for chapter 13, I've already done it for chapter 11, is I have posted some problems for you to try A lot of you didn't do that. They were due this morning, or they were due at noon today. All right, you should look for those things. They're not worth as much as the Alex assignments, but they definitely is some credit. And again, it's just a way for you to practice more things. All right, so look for that for chapter 13. It'll probably go up later this afternoon once I have time to put it together. All right. So, what's the other part of chapter 13? And really, if truth be told, this is the meat of chapter 13. We're going to talk about colligative properties. And the first thing we have to do is we have to define what a colligative property is. And a colligative property is a property of a solution that depends on the concentration of solute particles. All right, now we have to qualify that a little bit as well, because here's what we can think about. If I have a molecular solute, then what we can say is whatever the colligative concentration is, it's the same as the concentration of the solute. Because what we've said before is that if I have a molecular solute, that solute does not dissociate in solution. Okay, so for example, if I have an aqueous solution of glucose, then the concentration of the glucose is going to be the same no matter what, because the glucose doesn't dissociate in aqueous solution. It remains the same. Okay. On the other hand, if I have an ionic solute, let's do this in a different color. Then the concentration of solute particles is going to be some value I times the concentration or the original molarity of the solute. For example, if we dissolve copper 2 sulfate into solution, the concentration of solute particles is going to be twice the concentration of copper 2 sulfate. We ignore the water. The water concentration doesn't change, but the concentration of copper ions and the concentration of sulfate ions each are the same as the molarity that we calculated. Okay? We can do it with sodium chloride as well. If we take sodium chloride solid, we know from what we've learned before that if I dissolve that sodium chloride into water, then I get Na or sodium ions and chloride ions. And so what we would say is that in a perfect world, the I value for this solution would be 2, because for each mole of solute that I dissolve, I get 2 moles of solute particles, 1 mole of cations, 1 mole of anions. It changes for other ionic solutes. Now, our primary interest here is going to be this. What happens to molecular solutes? Because it's much easier to deal with those, all right? Because essentially what you say with a molecular solute is nothing happens. I is 1. So you're all set. Okay, so we talk about ionic substances with regard to colligative properties, but for the most part, our discussion is going to be focused on solutes that don't dissociate in solution. And one of the ways we do this too is we use non-aqueous solvents. Okay, we use solvents other than water, like methyl alcohol or benzene or things like that. All right, so let's look at these colligative properties in turn. And again, we're going to focus on the 3, there are 4 colligative properties in total. We're going to focus on the 3 later ones. We will talk about Raoult's law, but we won't do a lot of calculations associated with it. All right. So what is Raoult's law? It's very simple. The vapor pressure over a solution is proportional to the mole fraction of the solvent. That's basically what Raoult's law is. All right, now, if you remember back to chapter 10, what Raoult's law is essentially is an application of Dalton's law of partial pressures. It's pretty much the same thing. Okay, so here's an application. If I have a sample of pure water, based on what we've talked about in the previous chapter, that pure water is going to have a vapor pressure. Okay, we can figure out what that vapor pressure is based on the temperature of the pure water and knowing what the heat of vaporization is and such like that. We could figure it out using the Clausius-Clapeyron equation or just looking it up. If I dissolve some glucose into that pure water, what this is telling me is that the resulting solution would have a lower vapor pressure of water over it than with the pure water. Because the mole fraction of water, once I've dissolved glucose into it, is going to be less than 1. All right, so that's assuming that the solute does not contribute to the vapor pressure over the solution. Another way of looking at it is you could say, all right, the change in the vapor pressure of the solution or of the solvent is related to the mole fraction of the solute. All right, that's less often used, but occasionally it is used. All right. All right, now there's some problems with this, and one of the reasons that I present it, but I really don't spend much time with it, is that if you think about the derivation of Dalton's law of partial pressure, it's based on ideal gas relationships. Okay, if you want to go back and review that, you can go back and look in chapter 10, because Dalton's law of partial pressures is derived. It's fairly easy to derive, assuming you have ideal relationships. But if you think back to what do ideal relationships represent, they tell you that the molecules of an ideal gas don't have any volume. We know that's not true because liquids and solids exist. There's very little volume between molecules in a liquid or a solid. Second, there are no attractive forces between the molecules that make up an ideal gas. We just got through talking about intermolecular forces, which debunks that idea. And so you say, wait a minute. I'm taking a real relationship derived from something that assumes ideal behavior, which is impossible. How well does it work? That's a reasonable question. And here's the kind of thing that we see. Okay, in a perfect world, if I have a mole fraction of 1 for my solvent, then the vapor pressure of the solvent is going to be that of a pure solvent. Okay, that's what we see up here at the top of this graph. And if the mole fraction is 0, then the vapor pressure of the solvent is going to be 0. All right, what Raoult's law tells me is if I make a plot of mole fraction versus vapor pressure of the solvent, in an ideal situation, that's going to be linear. I don't need to know anything else. All I need to know is that what is the mole fraction and what is the vapor pressure of the pure solvent. And I have this linear relationship between the two. But that assumes that there are no attractive forces between the solvent and solute molecules. And that's one of the first things we talked about, is solutions exist because there are attractive forces between solvent molecules and solute particles. All right, so you can see there's a deviation. That's what this trace down here represents, is that deviation between ideal versus non-ideal. And so here's what we can think about. If we look at this graph a little bit more closely, what we see is that the deviation is least when the mole fraction of the solvent is high. All right, so basically what this is telling us is if we're going to use Raoult's law as a colligative property, then the mole fraction of the solvent should be greater than 0.9. All right, if we go much less than that, then we get huge deviation, especially when we're down in this 0.4 to 0.6 range. We get a huge deviation between ideality and reality with regard to this. Okay, now the other thing this graph doesn't show is this. You can also have deviations in the other direction, something like this, depending on the nature of the interaction between solute and solvent particles. All right. So it's all over the place. And so I find that Raoult's law is kind of a flawed thing. Now, it is used, and it was used for a long time to help determine molar masses. Now we're going to look at applications involving other colligative properties and the determination of molar masses, but not Raoult's law. Okay, my wife actually told me when she first worked in an organic chemistry lab, they used Raoult's law for molar mass determinations. And we will talk about those calculations, but again, we won't be using Raoult's law for it. We'll be using others. All right. Now, one other thing I want to talk about just in very general terms, because again, it has some practical relevance. And forgive me, but it has to do with alcoholic beverages again. Okay. You can tell I know a lot about these things. I've been making beer now for over 30 years as a hobby. And I've been learning some things about other production of alcohol in the process. I was in Italy last summer and I learned about wine production in Italy, which goes back thousands of years. You know, it's fascinating to think about in that regard because a lot of this stuff wasn't known when people started making alcoholic beverages, and yet they were able to do it masterfully for many centuries without knowing all the calculations. They just did it by trial and error pretty much. All right, so if I have two liquids, then both liquids are going to contribute to the total vapor pressure over the solution. All right, so the total vapor pressure over the solution is going to be the sum of the two liquid vapor pressures. And we can, by Raoult's law, assuming Raoult's law, we can calculate the vapor pressure of each of those components by knowing the mole fraction. Okay, so say for example, we have a mixture of water and ethyl alcohol. Then we could say the total vapor pressure over the solution is the sum of the two vapor pressures. And we can figure out the vapor pressure of each, or contribution of each component from the mole fraction, assuming ideal behavior. Okay, so if we have ideal behavior, then we see something like this. Again, we see a linear relationship between mole fraction and vapor pressure. Okay, in this particular case, though, it's the sum of the two. But here's the thing. With some solutions, you get deviation from ideality, something like this. Okay, you can see the pink trace up above. You get this bulge above that ideal line. Okay, and this is true with water and alcohol, but it's also true with other solvent mixtures where you can say, all right, I want to separate water and alcohol by this difference in vapor pressure. And so you start to distill. Okay, alcohol is more volatile than water, so it's going to have a higher vapor pressure. And so you say, okay, if I distill things right, I can distill off pure alcohol. But what this is telling you is you can't do that. You have a phenomenon known as azeotrope, where a certain mixture of alcohol and water actually has a higher vapor pressure than does pure alcohol. That's basically what this is saying. Or another way of stating that is, since vapor pressure is inversely related to boiling point, is that this mixture is going to have a lower boiling point than the pure solvent, because it's non-ideal. Alcohol and water like to stay mixed together. All right, now how does this affect us? Well, in New Jersey, you can buy a product known as Everclear. All right, and basically what Everclear states is that it's pure distillate from alcohol, from an alcohol distillation, but it's not pure alcohol. It's reported as 190 proof, 95% alcohol by volume. Okay, it's not pure. You can't distill pure alcohol, at least in the traditional method. You have to come up with some way to break that azeotrope to do it. And the reason I point this out is for health reasons. You can buy 100% pure alcohol. Okay, we have a couple of bottles around. It's sold that way. It is not sold for human consumption, because in order to break the azeotrope, most often the compound benzene, a known carcinogen, is used. And so you don't want to consume something that might even have trace amounts of benzene in it, because that increases the likelihood of certain types of cancer. And so if you go to parties where they claim to be serving 100% alcohol, you should challenge them. Where did you get this stuff? Is it really 100% or is it Everclear? If it's Everclear, it's probably safe to consume. But if it's something that claims to be 100%, I wouldn't touch it, because you don't know how that azeotrope has been broken. Now, another piece of advice is don't ever drink Everclear straight. It should be mixed with things. If you drink it straight, you run a risk of burning your esophagus, because it's too alcoholic, and it sucks the moisture out of your esophagus and out of your mouth as it goes down. Okay, enough consumer advocacy for the day. Let's talk about some more practical colligative properties that are useful. And again, you're going to put some of this to the test if you're taking Chem 126 this semester. So, in the last chapter, we talked about the phase diagram of water. And here's another view of that. This comes out of your textbook. You can see the copyright statement if you read it really carefully on the top. I'm using this with the permission of the publisher of your textbook, because I'm teaching from your textbook. All right, that's part of what you're paying for when you buy the Alex textbook combination. Okay, we know the phase diagram of water is strange because that liquid solid phase has a negative, or phase transition has a negative slope. Okay, and you see the phase diagram of water with the solid trace. Okay, so I can also generate the phase diagram of a solution, of a solute. All right, so For example, in this particular case, what I'm going to do is I'm going to make a 1 molal solution of glucose. In other words, if I take a kilogram of water, I'll dissolve 1 mole or 180 grams of glucose into that kilogram of water. The result is I get this second dotted or dashed trace. Okay, so we could say this is a 1 molal solution. What do I observe? What happens to the freezing point of this solution with respect to that of pure water? And what happens to the boiling point of this solution with respect to that of pure water? What is this telling us? Does the freezing point go down, or does it stay the same, or does it go up? What does the phase diagram tell us?
Stay the same.
Does it stay the same?
The freezing point decrease and
Yeah.
boiling point increase.
Exactly. The freezing point decreases and the boiling point increases. Okay, that's what this is telling us qualitatively. We see that decrease and increase. Where do we use this, practically speaking? It's wintertime right now. What happened last week? We had a potential ice storm on Wednesday morning. And as a consequence of that, what did the highway department do? And what did our campus maintenance do to prevent the likelihood of somebody slipping on the ice?
They put salt down.
Yeah, they put salt down. There's all this green stuff all over the campus right now. And at least Route 1 was covered in salt on Wednesday morning, okay? And this is a practical application of this very phenomenon. If you salt the roads, you lower the freezing point of water to the point where it'll melt. Okay, it also makes a mess. It makes your car a mess. It facilitates the rusting of cars. It's not so much an issue now as it used to be, but cars used to rust out after 10 years in New Jersey because they put so much salt on the roads. Okay, they've designed cars better so that they can stand up to that kind of thing a little bit longer than they used to. But you still can see rusty cars as a result of salting roads. And this is commonly done. And again, calcium chloride is often used because its I factor is larger. And we'll talk about that later on. Okay, so you have this freezing point depression. So what this is telling me is that a 1 molal solution is going to have a lower freezing point than pure water. And it also tells us that that 1 molal solution is going to have a higher boiling point. So we see both of these phenomena, and we can quantify both of these phenomena based on the molality of the solute particles in solution. So let's look at boiling point elevation first. The delta T of boiling, which is a positive number, okay? It's the boiling point of the solution minus the boiling point of the solvent itself. That is directly proportional to the molality of the solute particles. And so we can take that proportionality and turn it into an equation by using a boiling point elevation constant. So there's the equation that you use. If you have a certain solvent and you know the boiling point elevation of that solvent, or boiling point elevation constant of that solvent, you can either calculate the molality of a solution based on its boiling point, or you can calculate the change in the boiling point of the solution based on the molality. That's what this is telling us. Okay, we're quantifying what we have talked about in qualitative states above with the phase diagram. Similarly, we can look at freezing point depression. The one thing that's strange about this is kind of a strange definition, is we define the change in the freezing point as the freezing point of the solvent minus the freezing point of the solution. All right, it's a little weird, but that way it's a positive number always. All right, so again, that change in freezing point is directly proportional to the molality of the solute. And so again, we can turn that proportionality into an equation if we know the freezing point depression constant, or Kf, for the solvent in question. So if you're going to do calculations involving either boiling point elevation or freezing point depression, you have to have more data than just these equations. The equations are easy to memorize, and you definitely want to do that for the first exam. Okay, so far you have a number of equations that you need to remember. The Clausius-Clapeyron equation, some of the equations tied with cubic crystal lattices that we talked about on Wednesday, and these two equations. Right, you're going to have one more from this chapter, and that's it. When it comes time for the final, I don't expect you to memorize them. You'll have a sheet where they're written down. But on this first exam, it's not unreasonable. It's a way of you telling yourself that you've practiced this enough. All right. So if I'm going to ask you to work with these equations, I have to give you information like this. This comes from another textbook, but your text has the same sort of information. Perhaps not as extensive, perhaps a little bit different. Okay, so let's look at this. Let's look at water, since we've been talking about water so far. We know that the freezing point of water is 0 degrees Celsius. Basically, what this is telling us over here, there's the freezing point depression constant for water, 1.858 degrees centigrade per molal. That means that if I have a 1 molal solution of solute particles, the freezing point of that solution will be 1.858 degrees Celsius below the normal freezing point. So it would be negative 1.858 degrees Celsius. All right, that's what you have to remember. That's how far the temperature goes down. All right, so what else do we have? Well, we can see for water, the normal boiling point of water is 100 degrees Celsius. And the freezing point depression, the boiling point elevation constant for water is 0.512 degrees centigrade per molal. That means my 1 molal solution of glucose at 1 atmosphere would boil at 100.512 degrees Celsius, or whatever the Kelvin equivalence is. All right. One of the other things you want to remember, and I think we touched on this before, is that delta T in degrees Celsius and delta T in kelvins are exactly the same. Let's write it down. A delta T in degrees Celsius is the same as a delta T in kelvins. And so sometimes as a result of that, you find freezing point depression constants in kelvins per mole instead of degrees Celsius per mole. They are the same. Because of this. All right, so you can make that transition if you think about it. Most textbooks do degrees C per mole, and so you can use freezing point depression in degrees centigrade as well. Okay, and you can see there's a short list of solvents here. What are the most relevant ones as far as we're concerned? Typically, what we're interested in are solvents that have either large freezing point depression constants, okay, and benzene is a good example of that. Acetic acid is another good example of that. All right, but look at this, another one. Here's another one that's really an excellent one. We used to use this, cyclohexane. Look at cyclohexane. If you have a 1 mole solution in cyclohexane, it's going to freeze 20 degrees Celsius lower. So that means it's going to, if I have a 1 mole solution in cyclohexane, the freezing point of the pure cyclohexane is 6.55 degrees Celsius. We're going to take away 20 degrees from that. So that's 13.45 degrees Celsius below zero. It's really pronounced. And so back in the bad old days, we used to use cyclohexane as a solvent because it has such a pronounced freezing point depression constant. There are others. Okay, look at camphor. Camphor is 40 degrees Celsius per mole. Right, actually, I do remember teaching a lab many years ago where we used camphor. It smelled. Camphor has a very strong smell to it. Right, it's not an unpleasant smell and it's not unhealthy, but it's been deemed so. Okay, and that's the problem with cyclohexane is its vapor is not particularly nice to breathe. And it does have a pretty high vapor pressure at room temperature, and it doesn't smell very pleasant either. You can ask any friends that you have taking organic chemistry because they're actually going to work with it. It doesn't really smell that great. All right, what we've made the shift to doing, we used to use acetic acid as a solvent, but we had one colleague who was really allergic to it, and it also doesn't smell very nice. Okay, some people like the smell better than others. So we've gone to a solvent now called tertiary butanol, which doesn't have much in the way of smell. It's not particularly harmful, and it has a fairly large KF value as well. I think it's 8.3 degrees Celsius per mole. Okay. Water is not particularly good because it's kind of in the middle as far as its KF value is. Notice how ethanol is conveniently avoided. Ethanol does have a freezing point, but it's not in a reasonable range to use in a laboratory, so the book just ignores it. The same is true with carbon disulfide. Okay, so essentially what you can think about is what we can do with this is one of two things. We can calculate the freezing point of a solution using KF values, okay? Or we could calculate the molality of a solution by knowing the KF value and the change in temperature of the solution freezing point versus that of the pure solvent. And that's actually what you're going to do in lab. How are you going to do that? Something like this. All right. if you have a solvent that freezes around room temperature, okay, cyclohexane would be a good example of that. Um, that's why one of the reasons we choose tertiary butanol as well is because it freezes at 25 degrees Celsius or thereabouts. You can use an ice bath to get this stuff to freeze. And the same is true with cyclohexane. That's how we used to do it. Just put it in an ice bath and stir it, okay? And the reason you stir it is to prevent supercooling, which is another phenomenon that occurs. All right, and then of course you can monitor the temperature over time and generate a cooling curve. All right, that's something you're going to cover in lab. Let's talk about the last colligative property, and then we're going to get into some calculations in whatever time we have remaining, which probably is going to spill into Wednesday. So let's talk about the fourth colligative property and its implications, and then we'll get into the calculations associated with these colligative properties when we meet live on Wednesday. All right, so the fourth colligative property is known as osmotic pressure. And here's how you think about it. This is a very important colligative property, especially for our survival. Because if you don't think about this when you inject things into people, or you inject certain things onto nerve endings, the result can be extremely painful or deadly, depending on the circumstances. Okay? Presumably, you've heard before that it's really important in the human body to maintain, number one, temperature. Okay, that's why when our body temperature changes, we get sick. And number two, to maintain levels of electrolytes. Okay, if you exercise, this is something you need to think about. You have to maintain electrolyte levels. You want to take in salt if you exercise a lot. You want to take in other minerals if you exercise a lot. Right? And one of the reasons for this is because of this phenomenon known as osmotic pressure. Within the human body or within any organism, there are lots of examples of selective membranes. Okay, cell membranes, for example, are selective. Skin is a selective membrane, and things like that. Essentially, what you can think about is that certain substances can diffuse through these membranes and others can't. Now, water molecules are very small, so they can easily diffuse through a lot of things that other things can't. All right? For example, in this case, we're looking at glucose. Glucose molecules are much larger than water molecules. So if I have a membrane that's semi-permeable, the water molecules can probably diffuse through it, but the glucose molecules can't. It's a selective membrane. Now, if I have a situation where I have a difference in concentration across that membrane, then the phenomenon of osmotic pressure is going to exist. And essentially the way it works is like this. If I have pure solvent on one side of the membrane, there's going to be pressure for that to move through the membrane and dilute the solution that's on the other side. That's the phenomenon of osmotic pressure. And it's kind of shocking how large that is. There can be a huge amount just based on a small gradient of concentration. All right, so here's one way of thinking about this. And I remember having this illustrated to me when I was in high school. My high school biology teacher took a device that's known as a thistle tube, and that's essentially what this is. Okay? People used to steal them and make bongs out of them as well, but this was one of their primary illustrations was as a funnel or as an illustrator of osmotic pressure. And what he did was he filled he covered the top of the thistle tube, the wide opening, with a piece of sheep's bladder. Okay, a semi-permeable membrane. And inside the thistle tube, he put in a solution that had red food coloring in it and glucose. And then he dipped it into distilled water. And you could watch the column of the red solution going up the thistle tube. Okay, it started out, it happened fairly quickly, but then he left it overnight, and we came back the next day into class, and the column had gone way up, about 3 feet. And he said, well, I can keep adding tubing to this, and it would run up to the ceiling because the osmotic pressure is so high. But again, the phenomenon is that the water molecules are going to diffuse into the solution and dilute the solution. And the objective is to equalize the concentrations of the two solutions. So by diluting the solution of glucose, you do this. And there's pressure for molecules to diffuse through like that. Okay, now, osmotic pressure depends on two things. This large Greek letter pi represents osmotic pressure. It's equal to the molarity of the solution times the universal gas constant R times the absolute temperature of the solution. So what you can think about is osmotic pressure is going to depend, 1, on the molarity of solute particles, and 2, on the temperature. And what you can think about is the origin of this equation is actually this. PV equals nRT, where if you take number of moles of something and divide it by volume, that gives you the molarity. So this is the third equation that you need to memorize from this chapter. The osmotic pressure of a solution is equal to the molarity of the solution times the universal gas constant of the times the temperature. All right. So we're almost out of time today, so we're going to have to pick up on this next time. Really quickly before we go though, I want to illustrate one more thing. And this is something you have to think about if you're injecting into solutions into patients. All right. If you give an IV to a patient that does not have roughly the same concentration of solute particles that is naturally in the blood, you can cause problems with regard to red blood cells. Okay? That's what's being illustrated here. If I inject an IV solution that is isotonic, that means whatever concentration outside the blood cell is going to remain the same as what's inside the cell membrane of a red blood cell. Okay? If I inject a solution that is hypotonic, say for example, I inject distilled water into the vein of a patient, I can cause the red blood cells to rupture because there's going to be osmotic pressure to equalize the concentration of solute particles inside the red blood cell versus outside. And that's going to put pressure inside the cell, and it causes the red blood cell to expand. So hypo, meaning below. And if I do the reverse, if I inject a solution that has a higher concentration, then I create osmotic pressure moving out through the cell membrane, and I can cause a red blood cell to shrivel. Neither of these are good. Okay, it will cause red blood cell death, it probably will cause pain. The other thing is osmotic pressure plays a role at nerve endings. If you've ever had a broken tooth or a deep cavity and you eat sugar or salt, it is excruciatingly painful for that same reason, because you have this osmotic pressure gradient on the nerve ending in the tooth. It's not pleasant. Okay, so we'll pick up with some calculations on osmotic pressure and on freezing point depression when we come together on Wednesday, and then we'll look at some review sheets. Actually, look for the review sheets on chapter 11 on Canvas, okay? We'll post solutions to those later and some videos where I go over them. And then on Wednesday, we'll look at some review sheets for chapter 13 as well. All right, have a good afternoon.